Okay, so just to remind you, here is our little game here. We have just to do a quick recap of the previous video, Markov decision processes. We have a set of states here for our game that represents all possible locations of our robot. So here's one state, and this is actually what we call the start state or the initial state, which is the kind of the initial configuration of our game here. Next is we have the set of actions for our Markov decision process. We can go either up, left, down, right, and then not move at all. And finally, or we have two more things after this. We have a transition function that tells us the probability of taking the correct action. And what I mean by that is, for example, we might have something, we might know something like, well, our robot will take the right action 80% of the time, but 20% of the time we move in the wrong direction. So it might say like, well, 80% of the time when we tell a robot to move up or tell a robot to move right, we actually take those actions. But maybe 10% of the time if we tell a robot to move up, it'll actually move to the left, and the other 10% of the time when we tell a robot to move up, it'll actually move to the right. So the transition function kind of encodes all this, and you know the transition function ahead of time. You're given that ahead of time. And then finally there is the reward function. And the reward function, for example, in our game would be, well, if we end up in the green square, then we have a large positive reward. Or if we end up in the red square, then we have a large negative reward. And so the reward function is also something that you're given ahead of time. So you have all this information, this a priori information about our game, and we can try to figure out which sequence of we want to figure out the policy, and that is what sequence of actions should we take given the state that we're in to give us the highest reward here. And so we're going to be discussing a particular algorithm for this called value iteration. So here is value iteration. Now this equation at the bottom looks kind of messy, but I'm going to explain it in more detail actually in the next slide here. So just be patient with this, and we'll see this in the next slide. So kind of the notion is for value iteration is for each state, for a particular state, S, we want to figure out the expected reward of starting at state S and then taking the best possible actions at state S here. And so what I mean by that is we're in a particular state, and the value at that state, which is why it's called value iteration, the first part of value iteration at least, is we want to know what reward can I expect if I'm in this state and I act optimally. That's what the value of each state is supposed to represent, this V star of S. That's what that is representing. And this equation at the bottom is one of the Bellman equations. It's very famous, and it's used ubiquitously in reinforcement learning. And we're going to be discussing it kind of in more detail, actually, a bit, like I said, very soon in the next slide, because it looks kind of bad, but it's really not that bad. I'll explain it. And so with our value function here, based on your intuition, you can figure out that the value of states near high reward states will also be large, because if we're in a state that's right next to a high reward state, in other words, we're next to like a green square, then the expected reward of being in that state and taking the optimal action is going to be a large value. Now notice you have this discounting factor here. We have a discounting factor here, and that's at gamma, and this discounting factor represents a decrease if it's between 0 and 1, a decrease of the overall value function. In other words, we want to make sure if we have a value between 0 and 1, then we're basically discounting the expected reward as we progress. And so this kind of helps enforce the notion that we want to quickly get to the high reward state as soon as possible. That's kind of what that is representing. Now, notice that if gamma is equal to 1, if our discounting is 1, then there is no discounting, and we just want to get to the optimal state. Might not necessarily be prioritizing how many steps we do it in. And so, like I said, I'm going to explain this in more detail actually right now. And so it really isn't as bad as it looks. So let's first consider, let's kind of go inside and then move outside. So in the brackets, we are in a particular state S, we took an action A, we went to another state S prime, and the quantity in this brackets tells us the current reward for taking that transition, as in being in a state S, taking a action A and going to state S prime, plus the discounted future reward, because remember this V star of S prime is the expected value of starting at state S prime and acting optimally. So this is kind of like recursively defined here. So that's all this thing in the brackets is telling us. It's saying, at this point in the brackets, we're in a state S, we've taken an action A, we're in a state S prime here, and this tells us the reward for doing this transition plus the discounted future reward here. And so that's kind of this. And so now let's kind of move outward. And so now we have a transition function and this sum. And this sum is actually computing what's called the expected value. Because remember that we're non-deterministic. So taking some action A, we might end up in a number of different states S prime. There are a number of different states that we could actually end up in, and so we're taking the expected value of that, of that entire, of this action here. And so that's what the sum over S prime is supposed to represent. If we take an action A, it's not necessarily that we end up in this particular state S prime, remember, because there might be like an 80% chance that we actually move to the right, but there might be a 10% chance that we move up and a 10% chance that we move down also, and so that's what that's trying to encode. So in our particular game, the sum will be over three things, because there are three possible states that we can get to by taking one action. And so that's basically what the sum is computing. And so this is computing an expected value, and the probability is this transition function, and the value is this quantity in the brackets. Remember, we take this sum, we're taking this expected value because of this non-determinism. A particular action may end us up in several different states. Now, if we knew for a fact that taking an action will guaranteed 100% put us in this state, then we wouldn't even need this sum here or this transition function here. Okay, so now we're kind of at this point of this sum here. All right, and so now we'll finally have this max A here, this max action. And this just says that everything in the brackets here, out of all possible actions, we only care about the action that gives us the maximum of this maximum future expected reward. That's really all we care about. There might be actions that we take that give us a smaller reward, but we don't care about those. So that's why we're taking the max over all possible actions here. So this is saying that this is saying that out of all possible actions that I could take, I only want the one that gives. I want the maximum future expected reward out of all possible actions that I can take. So it's kind of a mouthful, and please ask questions about this. If you do, this Bellman equation is quite fundamental to reinforcement learning in general, and so hopefully this kind of helps explain a little bit about it. So this equation isn't as bad as people make it out to be. It's actually not too difficult to understand here. This is a little abstract here, so why don't we actually get to for our particular case, for our robot here, here's an example of a state, and here's an example of another state, and so here's an action that we take. We're saying go to the right, and it turns out that, well, 80% of the time the robot actually does go to the right, and so this transition value would then be, for this particular state, would then be 0.8, and then we have some reward for doing this. And if instead we moved up, then maybe it would be 0.1, and then this would be moving up, and then we sum across all those possible values. We take the expected value, and then we take the maximum out of all possible actions. So maybe moving right wasn't the action that led us to the maximum expected reward. Maybe instead of going to the right and up, it's actually better to go up and to the right. And so that's kind of what we're trying to get at by taking this max. And obviously they're invalid states. Like if I'm in this state, I can't move up because this is an invalid action. And so that's kind of how that works in terms of our simple game here. So here is our here's our actual value iteration algorithm, and it's really just repeatedly calling that Bellman equation. It's just repeatedly updating all of the values. And so initially what we do is we initialize all of the values to 0 except for the reward state. So we know what the reward states are, and so those we don't have to initialize because we already know what their value is. And then simply while not converged, for each state we compute this, we run this equation here, and we kind of keep. I'm going to show you pictures of how it actually progressing, and so we kind of keep iterating on this algorithm. So k tells us which step we're at, and so this is kind of it's a little confusing because it's both recursive in the sense that vs and there's vk and then vk s prime, and it's also iterative in the sense that here's vk to compute the next iteration's value. You need the previous ones, so this can be a little confusing here, but I'll show examples of this in a second. And by the way, what I mean by convergence is that I mean that the values don't change much. So after you run this for several thousand iterations, you're going to find that the values aren't actually going to change much. So in other words, they've converged. And by the way, the values are actually guaranteed to converge mathematically. There's a proof of convergence for value iteration. I've omitted that because it's kind of complicated. But let's actually go ahead and look at some of these some of the value iteration stuff here. So after 0, we have nothing going on here, and then after a single iteration, we know what our goal states are. So this is going to be a reward of 1. It's going to be a reward of -1, and then after another iteration, you see that here we're kind of moving outward. Here we're saying, well, how do you compute this value here, and we can compute 0.72 here, and as we kind of keep going after 100 iterations, we kind of figure out what values, which path we should take. So it does turn out that going up and to the right gives us, produces a better answer than going to the right and up. And so these arrows point to what the optimal action to take is. And so this is kind of the values here represent the future expected reward. So if I start here, then I know that if I start here and take the optimal action, I'll have a future expected reward of 0.49. And so I can kind of keep following this path, and that gets me to this reward here. And so what's actually going on here is we're also doing policy extraction. So remember that for value iteration, we just get we just get the values. We don't know which action to take yet. So that's a separate step called policy extraction. And so with policy extraction is after value iteration, we still need to extract the policy. And this is pretty much you'll see this bottom looks exactly the same as the Bellman equation, except instead of taking the max, we take the argmax because we want the action that gives us we have the action or the argument that maximizes this expected reward. So essentially, this is like a one-step look ahead kind of thing that's going on. And this is kind of because this is not that great, because we're essentially recomputing these values for each state again, and it's unless you can cache these to make it a bit more efficient. But essentially, we have two steps here. We have policy extraction, and we have value iteration and policy extraction here. And so the two steps, you have to do them one after the other. So after you've learned what the values are and the values have converged, then you run policy extraction to figure out which path you should take, or which action you should take in each state. So there are some issues with value iteration, and one thing to also mention is policy extraction is like a separate independent step. So that just kind of seems to waste the notion that we have all this information about our values, and yet policy extraction is a separate step. That seems kind of wasteful, and so that's kind of an issue with value iteration. Another issue is that the policy may converge sooner than the actual values. And what I mean by that is we might know which path to take. The path to take might to get to the maximum reward might not change for hundreds of iterations, but the values are still changing just a little bit. So we haven't quite converged yet, and so that's also not too good. It's again being kind of wasteful of our resources. There is a solution to this, and I'm not going to get it into, called policy iteration, and that's kind of like value iteration, except instead of iterating across the values, you look at the policy itself. But again, we're not going to get too much into that. The biggest issue with value iteration that is why why we need something like Q-learning is we assume that we have perfect knowledge of the transition and the reward functions, which is not true in real world scenarios. Think about, learning something new. You don't necessarily know what actions are or what is good or not. You have some overall notion of what's good and what's bad, but you don't know that if I do this, if I press this button, then I'm going to get a good reward. And so assuming this perfect knowledge of the transition and reward functions is not true overall. And so this is why we need something like Q-learning. And so we're actually going to get to Q-learning in the next video, but I just want to do a very quick recap of what we discussed. In particular, we discussed this notion of value iteration. And for value iteration, right, the idea is that for each state we figure out what the expected reward is of starting in a particular state and then acting optimally, taking the optimal actions. And so you can see here we can kind of get these values here, right? So essentially what we have is after these values converge, then we can run the second step called policy extraction. That'll actually give us the actions to take that will lead us to the best state. And so then we discuss policy extraction. Then we kind of discuss some issues with value iteration. In particular, the biggest one is we have perfect knowledge of the transition and the reward functions, which we definitely don't have in the real world. And so that's coming up. We're going to discuss Q-learning and how we can kind of discard that assumption by repeatedly playing the same game over and over again. And so in the next video, we're going to get more into Q-learning.